All right, thank you for having me here. Good morning. So I'm going to talk about what we are doing with generative AI right now in our product. And one of our products basically involves cloud cost monitoring, cloud cost management. And cloud costs are most companies use the cloud today. Managing the cost of the cloud is a hard task because basically it's democratizing the use of resources across organizations. And if you don't do it, it actually costs a lot more money than it should. So using these kind of tools, whether they're the cloud-native tools for cloud cost management or from other companies, is really critical. Our approach for cloud costs is what we call the autonomous intelligence model. It has multiple layers. The first layer is to bring visibility to the costs of what's happening, who's using what, and how much does it cost, and are they using it wisely? Then providing insights, and here we're using machine learning, classical machine learning algorithms for detecting anomalous behavior of the cost, forecasting costs, and those help in managing the cost better. The next layer is actually providing automatic recommendations of what to do to save costs. It could be turn off storage that's not used anymore, and it could be upgrade to a different family of servers that could cost less for the same workload. And the last part is actually having automated actions. So why have human in the loop for some actions? Why not take it automatically and save the costs and not have to wait for a human to do it? So all this is nice, and we've lived happily with this model for until a few months ago when generative AI came out. And then we said, okay, what can it bring us in this product that we didn't have before? So our main constraint is our UI. Well, our design choices and product choices for the UI and the UX of how users interact with their data. This is an example of a dashboard that shows forecasting. So we decided to show the forecasts in a certain way, in certain tiles. The user cannot change that if they wanted to ask something else. The same thing for finding anomalies. We have multiple ways of showing anomalies to the user. On the left is a Slack message. So this is how we formatted the message to send into Slack. And telling them, look, you have increased cost in some service that you're using. Maybe take a look and save that cost. Or in our UI. And all of those take a long time, take developers to do. And sometimes users come and say, no, but I want to see it a little bit differently. Or I want to ask different questions. This is the same thing, recommendations for how to improve the cost of the service. Again, we had to make design choices about how to group things together, how to show it to the user. And we hope, we of course have design partners, and it's a long process, and we hope that this fits most users, right? The 80-20 law. But users tell us they have many more questions that are either impossible to get from our system, from our UI, the way it's designed, even though the data is there, or it takes an expert to extract it. Questions like, list me the number of services the services that we launched this month that we didn't have before. How many EC2 instances of each family did I use last month? All the data is there, I promise you, but it's not easily extractable in the UI, the way we designed it. So another question I like, how many volumes moved from a certain family of storage to another family of storage last month? What's the % of GP3 coverage? Et cetera, et cetera, et cetera. So all these questions, for each one of these, we would have to design some UI element or have to think, do most customers want it? Do they not want it? And of course, as we add more and more of these elements into our product, the product becomes more complex and not necessarily better for most users, because now they would have to know all these different functionalities and find them. So this is where generative AI came and really helped us provide a mean to access all this data that's already there, that is indexed, analyzed, even insights on top of it for anomalies and forecasts, for example, and recommendations. But now we can allow the user an easy interface to get to these answers. So this is how it looks like in the product. Basically, simple chat interface. A user can ask a question, get the answers below with some visualization, and everything becomes much, much nicer and better, and they can ask really complex questions. Now we can also create it, we can make it available not even in our UI, we can make it available in other tools. So this is an example from our Slack bot, where the user can ask, what were the services that had the most anomalies in the last month compared to the previous month, in June compared to May. And this is a question, the data is there in the database. We wouldn't have thought to create a UI element to answer this question, but now when a user can ask this question, they get an answer, and they get very interesting answers that tell them what they need to know about their data. Now, how do we do this actually? How do we answer questions about data? And the previous talk talked about data privacy. Of course, this data is owned is stored in our servers, but it's owned by the companies that are actually making these spends. So our customers. We cannot let open models or external models get to this data. So the mechanism by which we actually get this data is by asking, in this case, GPT-4 to create SQL queries. SQL queries on top of the data, and what GPT-4, and this is the SQL query for that question that you just saw. So, it's not the most complex SQL query, but if you had to give an analyst the access to this will be, this will take a little bit of time to write. But with GPT-4, with a large language model, you basically get this answer after a few seconds. And it's actually correct. It creates a whole SQL that then we can run on the database and provide the answers to the users. So what's the solution high-level architecture? Basically, we have two flows. The flow that asks questions about the data, and flows that asks more general questions that are about the domain of cloud cost management. And this is a template that's actually we can see in almost any domain that has data behind it. The first thing, a user asks a question, we make a determination with a large language model, whether it's a data question or a general question. And then we take two different flows. The first, the flow that asks about data, we cannot provide the data to the large language model unless we we train our own. So we send a question asking to create the query, the SQL query. And once we get the queries, we can validate whether they are valid, whether they return results, whether they return errors, and iterate with a large language model if we find issues. Well, if the system finds issues, and then provide the answer after deciding on a visualization. The other flow basically takes a whole corpus of knowledge about the domain, in this case, cloud cost management, and there are books about it. There is a FinOps organization that has a lot of documents, and basically the web is full of those. We store this information, chunk it, embed it, and put it into a vector database. Why is that helpful? Because whenever somebody asks a question, we want to add context to the question that is more domain specific. And basically by taking the question and finding what context from the entire corpus that we indexed in the vector database is relevant, we can add into the prompt to the large language model the question and the domain context, which helps produce much, much more accurate answers. So what are some key points that we saw that make this accurate, make it work more accurately? So first of all, we started out with GPT 3.5, and 4 is much more accurate at creating SQL queries. So if you're trying it yourself, I would recommend using 4. Besides the version, the specific version of large language model, context is the king in this scenario. If you add domain-based context, if you add internal knowledge, and if you add feedback, you get much better results, and very quickly. I might ask. You know, it's very. So this is some example of context that's important for asking questions about the data. So first of all, we have to provide the schema of the database or the tables that we want to write SQL about. Otherwise, the large language model would have no clue what it means. If the column names are interesting, like dates, they say the word date, then the large language model understands this is a date column. We don't have to specify. If the names of the columns are not so clear, adding context of what they mean is really important. For some columns, you might want to add the values, the potential values in that column. For example, service names in AWS, if you add, and there is a column called service, if you add the service names as a list to the large language model, it knows much better to answer a question when somebody asks, what is my S3 usage this month? Otherwise, it would not necessarily know how to create the correct query. Another interesting example at the top, AWS provides ARM servers and Intel-based servers. If you want the query, if somebody asks, how much am I spending on Graviton servers versus non-Graviton, the large language model needs to know something about what it means to be Graviton or non-Graviton in the data. So providing a list of how to identify a Graviton server is important as well as part of the context. So these are just a few examples. The second point that we saw that really helped make it work accurately is few-shot learning. Providing, even as part of the context, even before fine-tuning a model, just a few examples, good examples and bad examples of queries goes a very long way. It's incredible how very few examples in the context make it work dramatically better in creating the right SQL. So here's an example question. What were the services that had the most anomaly impact increase in June compared to May? That's the previous question that I showed. And if we run it multiple times, we sometimes get different answers. So you see the answer on the right, the answer on the left, they're different. Now, what we determined by looking at the SQL is that the answer on the left is actually not the answer we desire. It's not a wrong answer, but it's not the answer that we like and the users like. And the reason is by looking at the SQL, so it produced two different looking SQLs, but they're actually almost the same. And if you look very carefully, the only real difference between the two is what it used to determine when an anomaly occurred. And it turned out in our database, we had two columns, a start time for an anomaly and an end time to an anomaly. And one time it used the end time as the column to determine the time of the anomaly, and one time it determined the start time. Those sometimes, the start time could start in May and end in June, and of course that will produce really different results. So by letting the model know, okay, inspecting the results and providing a little bit of feedback saying, this is a good example, this is not such a good example, we actually help it produce very reliable and robust results afterwards. And it really doesn't take a lot of these to get the results you want. So what's next? So we're constantly improving the system, and also the industry is changing constantly and giving us a lot more tools to rapidly advance this. One example is, which we are implementing, is letting the LLM decide, based on the format of the result, how should we visualize it? As a graph, as a pie chart, as a bar chart? I mean, there are lots of different options of how to visualize the data, maybe as a table. So actually we are asking the large language model what would be the best visualization, and then we're implementing it. So again, we're not giving them the data, but we're giving them the format of the data. All of this right now is just simple prompting to the large language models. But as we advance this, these will involve a lot of small agents, each performing different tasks, asking different questions from the type of data that we hold behind the scenes, and then combining them into one single result. An interesting thing that what we're already doing is integrating the specialized machine learning models that we have for anomaly detection, for forecasting, basically time series based models, with the large language models by having them interact with each other. And of course, this blueprint does not involve just cloud cost optimization. It can be extended to any type of BI scenario to produce answers. And what seems to be very important for this to work is to have it, to have the context of the domain that is involved as part of the either prompting or the agent that you're building. So with this, I'm done, and I'll take any questions. Thank you.